All right, good morning. Happy Monday. It is Monday, right? It feels like a Monday. All right. Just to remind you where we left off, it always feels like it's a long time from Thursday to Monday. So we had started talking about light, what we also call electromagnetic radiation. Okay, so visible light is only a small portion of the electromagnetic spectrum. And there's microwaves, ultraviolet rays, gamma rays, X-rays, radio waves, all of that. That all makes up the electromagnetic spectrum. We talked about frequency, wavelength, and how those were related. We're going to get into energy today, and hopefully that will then lead us to different models of the atom. Okay, so just to get the main point here, the study of light, and in particular light emitted from atoms, allowed scientists to figure out more about the structure of the atom and where the electrons were. So that's where we're heading. Make sure that you sign in for attendance. The attendance sheet is going around. We're kind of on what I consider a normal week this week. We have homework due on Saturday again. I don't have quiz 3 up yet, but that should be coming later today. Homework 3 is up. There's also an adaptive quiz for chapter 4 up already as well. Don't forget about office hours. You do get 1 point for each attendance. And our first exam is next week, next Thursday. Okay? So next week is going to be a little bit of a different week. We'll probably have a homework assignment due that week, but there won't be a quiz because you're going to be taking an exam instead. This week as well, I will start posting some practice material for the exam to help you get ready. Study guide, some practice exams. We'll see, maybe some additional information in Achieve. We'll see what comes up, but there will be different practice stuff. Yes, Brandon? Is the exam going to be on Achieve too? No, the exam will be in here on paper, assuming we're still in person, which I hope we are. Yes?
So the exam, study guides, and practice, is it going to be on BB Learn or Achieve?
Probably in BB Learn.
Okay, thank you.
It's probably just easy. There's enough stuff in Achieve, and I don't want to clutter that up. I kind of want to keep that for homework, quizzes, pre-lectures, and then things that I just need to post, I will post in Blackboard. Okay? Other questions before we officially get started and back to material? No questions? All right. It wouldn't be chemistry without a chemistry joke to start our day. If I can find the... Oop, that's a little bit small, but hopefully you can see that. I know there's another chemistry joke. It's on the tip of my tongue, Sten. Oh, that one's sad, Element jokes, it's on the tip of my tongue. All right. You guys are a tough crowd. All right, so let's just back up, do a little bit of review from last Thursday. And again, stop me at any point if you have questions. We're going to do some calculations early today, and then hopefully we will get through some theoretical things about the structure of the atom. So, again, light. The reason why we're covering this right now is it helped us figure out where the electrons were, in particular in the atom, more about the electrons. And so we talk about the wavelength of light, the distance between two waves. Okay. Typically, we'll measure that peak to peak. That's probably the easiest way to do that. And then frequency is the number of cycles of that wave per time. And typically, our time unit is second. Okay. So always think about the more cycles per second, okay, the more times that wave is oscillating. Now, actually, there's 2 oscillations. There's an electric field oscillation and a magnetic field oscillation perpendicular. The more oscillations per second, the higher the energy. Okay? The energy, and this is a key point, does not depend on the speed of the electromagnetic radiation. because all electromagnetic radiation is traveling at the same speed. Is everybody cool with that? So what is that speed? Not a number. What do we call it? Speed of light. Okay? So we generally think as an object is traveling at a higher rate of speed, that's more energy. And that's true. But in this case, all forms of electromagnetic radiation, whether it's visible, X-rays, gamma rays, they're all traveling at the same speed. So what determines the energy is the frequency. Higher frequency, more oscillations per second, more energy. And if you have more oscillations per second, so look at this bottom wave, more oscillations per second, higher frequency, thereby you're going to have a shorter wavelength. Okay, so those are inversely proportional. High frequency, short wavelength. Okay, so make sure you have the qualitative relationship, and then the quantitative piece, as we looked at last time, is that piece there, the speed of light, so that letter C represents the speed of light constant, is just the frequency, which is the Greek letter nu, kind of looks like a V, and then times lambda, which represents the wavelength, and so a nice simple equation. Okay, so make sure you know which one of those is frequency, which is it's the first one that kind of looks like a V, and then lambda is the wavelength. C is the speed of light constant. All right, any questions just on the review there? We good with frequency, wavelength equations? All right. All right, let's get the next slide. So we can go further. As I just hinted at, the energy of electromagnetic radiation is proportional to the frequency. Higher frequency, higher energy. And we see that in this very simple equation. If my frequency goes up, so if my frequency is higher, larger number, what happens to my energy? Energy goes up. Those are, frequency and energy are directly proportional. Okay, high frequency, high energy. Very simple equation. There is a proportionality constant, H, which is called Planck's constant, and that's named after the German physicist who came up with this equation. Okay, just by looking at radiation coming from different objects. Okay, so energy, frequency, and that's Planck's constant. There's a picture of Planck. Now we will do some calculations here in a minute. Look at that equation that you see there. That just comes from the one we had on the previous slide. Okay. So if we want to solve for frequency, we can just divide by wavelength. Okay, which is shown here as well. A little more difficult to see with the slash like that, so I like to write it like this. And if we want now, we can plug in up here and come up with the relationship between energy and wavelength. Everybody with me? We're just substituting in. We're going to substitute for frequency in that top equation, and we're going to have a relationship with wavelength. Plug that in, and we end up with that equation. And let's write it again a little bit differently, just so we make sure to note that wavelength is in the denominator. Yes?
I'm sorry, I haven't looked at so the second equation that you wrote in green, that's just the equation that we learned previously with the constant.
Yes, this one here.
And then what? So how are you? Oh, okay.
So what we're going to do with this equation, everybody's good with this equation, right? This is just relating frequency and wavelength, speed of light constant. We just solve that equation for frequency. okay? So frequency is speed of light divided by wavelength. And now we're going to take that, c divided by lambda, and plug it in for frequency in that top equation. So then we end up with h times c over lambda over wavelength, okay? Anything else while we're here? Okay. So let's look at this equation very quickly, just in terms of energy and wavelength. If my wavelength gets longer, larger distance between waves, what happens to my energy? Lower, right? Because I'm dividing by a bigger number. It's going to make my energy smaller. Okay, so longer wavelength, longer distance, hang on just 1 second. Longer distance between waves, lower energy. And we saw that in the previous slide, right? High frequency, short wavelength. Low frequency, longer wavelength, and that's going to be a lower energy. Yes? Yes, so I will give you all these equations that you've seen and all the constants, those will be on the equation sheet. So another thing that I will post before the exam, and that's a good reminder, I will post the equation sheet, okay? So you'll know what's on there before the exam happens. But I don't, it doesn't make any sense. I'd rather you learn this material, and I don't want you memorizing constants. I don't want you memorizing equations. Not that these are particularly hard equations, but you get on an exam, exams have some pressure associated with them. You might just go, wait, is it hc over lambda? Is it h over c lambda? Whatever, I don't want you to do that. So I will give you an equation sheet. You'll see it ahead of time. Of course, you'll also have a periodic table with the exam as well, okay, because that's a tool that we will use throughout. All right, other questions before we move on? Okay, so just to sum up, I want you to know both qualitative, how are frequency, wavelength, and energy all related without a calculation. Okay, high frequency, short wavelength, high energy. Low frequency, long wavelength, low energy. So that's the qualitative piece. And then we will plug into these equations. They're relatively simple, but you do have to watch units a lot of times. So we'll do a calculation here on this next slide. So here we have, remember, and we're not going to go into this in great detail, but when we get into these very small, what we call quantum particles, they also have wave-like properties. So light, depending on the experiment, sometimes has wave-like properties, sometimes has particle-like properties. Sounds odd, but that's how quantum particles behave. And so a photon is just a particle of light. So we'll talk about photons of light. Frequency of 7.5 times 10 to the 14th hertz. We talked about the unit hertz last time. What is the wavelength of this light? What color is this light? Now I will show you a visible spectrum in just a minute. And what is the energy of this photon? So let's put a little more information up here. You know that equation. Okay. So go ahead and take your time, solve for wavelength just to practice this. You don't necessarily have to rearrange the equation first to solve for wavelength, but you might want to do that. And then you might hopefully still have in your notes speed of light constant 3 times 10 to the 8th meters per second. So go ahead and plug in and see. Does everybody remember what hertz means as a unit? Per second, 1 over seconds, or inverse seconds, however you want to think about it. All right, so let's plug in. And I'm going to show this calculation on the calculator just to make sure you're doing scientific notation correctly. This is just plug and chug, right? It's not too bad. We plug in the speed of light constant. That'll be given on the exam. We plug in the frequency that's given. You do have to rearrange the equation. Solve for wavelength. Note your units. Seconds will cancel. And is that what you expect for unit of wavelength? Yeah, we expect a distance, right? Wavelength is distance between two waves. All right, so wavelength is a distance. Okay, and we'll do this conversion here because for a lot of wavelengths, they're quite short. And this one, you should get 4 times 10 to the negative 7th meters. And quite often, we will convert that to a different unit, maybe nanometers, maybe micrometers, just depending on how small that number is. So let's do this calculation just to make sure we're all on the same page with our calculators. Okay, let's see. Zoom in a bit here. Okay. So we're going to go, let me make sure that's on the screen, 3, and then find your EE key, 8. So there's your speed of light constant, just 3e to the 8. And we're going to divide by 7.5 EE the 14th. Okay, so make sure you use that EE key. Most of you probably have TI calculators, so it's probably labeled EE. That's kind of a glare there. You can't see the 14th, but there is a 14 there. Let's see if I can get this better. There we go. If you have a Casio, it says EXP. I don't know what other types of calculators are out there, but find that key, and that's the way to input it, and then we just hit our equal sign. And there in scientific notation, 4 times 10 to the negative 7th. Okay. Everybody good with calculator? You definitely don't want to, on the exam, make calculator errors. Okay. That's, I haven't quite decided on the format of the exam. The exam will probably mostly be true, false, multiple choice, those kind of questions that are graded quickly. There will probably be a few problems that will be hand graded. So on a multiple choice problem, you don't want to miss it because you're not using your calculator correctly. All right, we good? All right, let's do our conversion here. To nanometers. And what does nano mean? 10 to the negative 9. So make sure you know your metric prefixes, right? So we have to know our metric prefixes for the exam. I'm not going to give you those. 1 nanometer. And then we just, oops, sorry. I do that a lot. I get looking at my computer and forget to look at the screen. Let's try that again. So we're going to convert 4 times 10 to the negative 7th meters to nanometers. So we want meters to cancel, numerator, denominator. We want to end up with nanometers. So remember we practiced unit conversions earlier in the semester. Here's a unit conversion. And then we're just going to write in the number for nano. This letter just means a number, and that number is 1 times 10 to the negative 9th. Okay? So we're going to punch that in our calculator, so let's go back. Okay, so there's the number that I had. Now, the 1 times 10 to the negative 9th was in the denominator, so we're going to divide by that. Divided by 1, EE negative 9. And I'm still in scientific notation, so you see 4 times 10 to the 2nd. Okay, which would probably be a better way to write it other than what we had up there, 400, which doesn't quite show our sig fig. So let's jump back. Okay. So note, on this slide, it was written as 400. That's probably not the best way to write that number. We should really write this as 4.00 times 10 to the second nanometers. Questions? Not too bad? All right, so that's the first part of this problem. So we've calculated wavelength. What color is this light? I don't expect you to memorize the visible spectrum other than you should know certainly the endpoints, 400 nanometers and 700 nanometers-ish. So let's look at our visible spectrum. So the low energy end, so let's start with the low energy end, longer wavelength. Lower energy, that's the red end of the visible spectrum. So you certainly need to know that. If I have a more detailed question like this, I would put this on the equation sheet so that you can actually see this. So low energy, red end, 700 nanometers. High energy, violet end, it's around 400 nanometers or so, maybe down to about 380 in that range, okay? So what's the color of this light? Yeah, it's going to be in the violet region of the spectrum. Okay, so an arrow did come down to point, a nice violet arrow to point at 400 nanometers. And then the last piece. Go ahead and use that equation that we just used previously and take your frequency, just practice one more time, and then we'll do a couple more calculations before we move on. Oh, we didn't do the calculation with this yet, did we? I showed you the equation. Okay, let's do, sorry, my brain's not quite there this morning. Let me give you Planck's constant. Okay, so this is a fundamental constant. You will see this in other equations if you go on in science courses. Fundamental constant, Planck's constant, 6.626 times 10 to the negative 34th. And the units for this are joules per second. Okay, don't need to memorize that. Okay, that'll be given on the exam. So we have the frequency that was given. Let's plug that in. Plug in Planck's constant. Just two numbers, multiply them together, and get the energy of a photon of light of that particular frequency. Okay, so we're going to take Planck's constant times the frequency, so 6.626 EE, negative 34th power, and then we're going to divide by, or not divide, multiply. Oops, that's not going to work. Let's try that again. Okay, multiplied by the frequency, 7.5 and hopefully I punched that in correctly, at about 4 point, how many sig figs do we have? Looks like 3 and 7.50. So 4.97 times 10 to the negative 19th. Okay, and this is going to be written over, but there's the calculation coming up on the screen. Okay, Planck's constant. Oh, I wrote joules per second. I'm sorry. I messed that up. I'll blame it on Monday, although that's not a very good excuse. Scratch that. It's joules times seconds. Sorry about that. And then when we multiply by frequency, which is per second, our seconds are going to cancel. Okay. And as you might, is everybody familiar with the energy unit joule? I mean, it is what's considered the SI unit of energy, System International. It is what scientists use for energy, the unit of joule. Okay, so that's what we expect. And as you saw, I'm not sure where the answer is. It's not going to show up, so let's write it down. All right. So sorry about that. That wasn't my best effort. But 4.97 times 10 to the negative 19th joules. Any questions on the calculation? All right. Look at that number. What do you think about the magnitude of the energy of a photon of light? Is that a really small number? Yeah, it's a really small number. So one particle of light, one photon of light, has a really, really small energy. Very, very small energy. Okay? So that's something to keep in mind, and I'm going to try to input a blank slide here so we can do some more calculations. But anytime you use this equation, anytime you use the one that we did with wavelength, E is equal to hc over lambda, that's the energy of just a single photon of light. And it's going to be a very small energy. Now, we might want to work with a larger amount of light. Okay? And we really haven't dealt with the mole very much this semester. We've hinted at it. But just for fun on a Monday, why don't we bring out the mole, okay? You know, they're such cute little creatures. So let me get out of here for a second and see if I can put a blank slide in here. Okay, let's see if that's going to work for me. Nope, didn't like that. So I need a pen. So there was our energy that we just calculated. Now, it doesn't show up in the unit. It does not show up in the unit, but make sure you realize that is joules per one photon. Okay, it's the energy per photon of light. So we could write our energy like that. Okay, you don't have to, but make sure you understand that when we use that equation, E is equal to h nu, that's the energy per one photon of light. It's just understood that that's the case. All right, the mole. How many things are in a mole? We talked about it, but that was a while ago. Yes?
6.022 times 10 to the negative 22nd?
Oh, you're close. So your first part of the number was right. Your exponent is not.
Is it the 22nd?
Anybody else help us out here? What is it? 10 to the 23rd. Okay. So in a mole of anything, there are a lot of things. Okay. Now, things might be atoms, might be molecules, might be ions, might be photons. Doesn't matter. It's when we say a mole, we mean a certain number of things. Okay. And the example that's always thrown out, if I say you have a dozen eggs, you know how many eggs that is, right? Okay, a dozen is 12. Well, for chemistry, one of the units we're going to use a lot is the mole, because atoms are really tiny. The energy of a photon is really tiny, so we need lots of things. Okay, well, that number of things is what we call Avogadro's number. So we typically label Avogadro's number capital N sub A, so N for number, A for Avogadro, and it's just 6.022 times 10 to the 23rd. Again, you don't have to memorize that, but you'll see that enough as we go on in this course. And then we typically write particles, okay? Again, particles. What do we mean by particles? Atoms, molecules, ions, photons, things like that. So just generic particle per mole. And I always love the abbreviation for mole. We just drop the E. Quite the abbreviation, right? So MOLE for mole, but we typically just write it MOL. Okay? So don't be afraid by that number. It's just like any other counting unit. Whether we say there's this many in a dozen, there's this many feet in a mile, it's just a given. And again, this number does come from somewhere, just to let you know it's just not made up. It comes from the number of atoms of carbon-12 in 12 grams. So carbon-12 is our standard for mass. Carbon-12 weighs, a mole of carbon-12 weighs exactly 12 grams. And in that 12 grams is that many atoms. Okay? So wrap your mind around that to get to 12 grams of carbon, okay, how much is 12 grams? Is it a lot? No. So again, we sometimes aren't very good with the SI system of units. 28 grams per ounce. Okay, so we might be more familiar with ounces and pounds and that kind of thing. But 28 grams in an ounce, so 12 grams is less than half an ounce. So less than half an ounce of carbon takes that many atoms to add up to that mass. Okay, so that should give you a feel for how small an atom is. They are really, really tiny, as you have been told, but try to get that mental picture is pretty helpful. All right, so what I want you to do here for me is do another unit conversion. See if you can convert from the energy of a single photon to the energy of a mole of photons. Okay, and you're going to need to arrange Avogadro's number to do that conversion. Attendance sheet make it to everybody today? Oh, it didn't make it to that there. Let's go and sign that right there. And again, with unit conversions, make sure you watch your units, arrange that conversion factor. Avogadro's number, we could change this a little bit if we wanted to and write per 1 mole. And remember, particles can mean photons, it can mean atoms, it can be molecules, whatever we need. All right, so let's write this one out. Again, unit conversions, a lot of times it's good just for practice to just write the units in first to make sure you have that part. We want to end up with moles in the denominator, the energy per mole of photons. Okay, so we want moles in the denominator, we want photons to cancel. Okay, so photons in the numerator cancels with photons in the denominator. Turns out Avogadro's number is already written correctly for this conversion. So there are 6.022 times 10 to the 23rd photons per 1 mole of photons. Okay, there's that many things in a mole of anything. And so break out your calculator as you already have. I still have that number in my calculator from the last calculation, 4.97 times 10 to the negative 19th joules. And now we're just going to multiply by 6.022 EE 23. So what'd you get? Okay, so I'm going to write it a little bit below the equal sign here. 2.99 times 10 to the 5th joules per mole. Okay, so it's everybody okay with that calculation? Not too bad, but that's bringing in Avogadro's number, which we'll use quite a bit in this course. What about the magnitude of that number? Now, we probably don't have a feel for, really the energy unit joules, but compare the magnitude of 10 to the negative 19th to 10 to the 5th, 10 to the positive 5th. Yeah, there's a huge difference, right? And that's 1 photon versus a huge number of photons. Okay? So 6 times 10 to the 23rd, that's a lot of photons. And now we're into an energy that we might expect if we had, a beam of light of some sort, okay? All right, any questions on this calculation? Before we move on, we're going to do another one. Lots of calculations today. It's a Monday, isn't it? I can just feel the energy. I'm not the most energetic today either, but, let's struggle through our Monday here. Particularly at 8 in the morning, right? 8 in the morning on a Monday, that shouldn't be allowed, right? It should be outlawed. It's like nothing should get done until at least 10 on a Monday morning. If I were president, that would, never mind. All right. All right, one more calculation while we're here. We have about 10 minutes left, so hang with me. Does everybody still have this equation? E is equal to hc over lambda in their notes. That was where we rearranged E is equal to h nu. So the relationship between energy and frequency, we plugged in wavelength, okay? So I want you to practice calculating energy from wavelength here. Let's back up. So look back, previous slide, or your previous notes. What was the wavelength of that violet light? Okay, 400 nanometers, or in meters, 4 times 10 to the negative 7th meters. Okay, so we have, and I'm going to write it in meters, and you will see why we need meters here. So let me write it up here because I'm running out of room. So there's our wavelength. We calculated that previously. Planck's constant, speed of light constant. Okay, don't have to memorize those, but you need to be able to find those and use those. They'll be on the equation sheet. Plug in your wavelength, solve for energy, and then compare that to the number at the top, because that's what we got from the frequency. Okay, and let me write down the other constants. You should have these in your notes. I'm out of room. Bummer. All right, so I hope you find that these equations aren't too bad. These constants, you might think, oh, that's such a small number and whatnot, but it doesn't matter. We just plug in the constants, those are given. Make sure you note your unit here of why I needed to plug in meters, not nanometers. We had solved for nanometers previously, but speed of light is meters per second, so I need my wavelength in meters. So meters now cancels, seconds canceled, and as you might expect for energy, we end up with joules. And we should end up with a number that's very close to the one at the top. So 6.626 EE negative 34 times 3 times 10 to the 8th divided by 4 EE negative 7, and we get the same number. (4.97 times 10 to the negative 19th joules). And that shouldn't surprise you, right? We solved using the frequency, and then we solve with the wavelength that we calculated from the frequency. We should get the same answer. Questions? Okay, so we still have about 5 minutes. I'm going to do a little bit more because we're going to start getting into models of the atom. But this is our last calculation for today. But what I want you to leave with today is know the qualitative relationships, energy, frequency, wavelength, and then know these really 3 equations, right? The relationship between frequency and wavelength, the relationship between energy and wavelength, the relationship between energy and frequency. So there's really 3 equations there. All right, a little bit more for today. Let me tell you a joke before we go on, just to liven up the last few minutes. So one atom bumps into another atom. Says, hey, I lost an electron. The other atom says, are you sure? Says, yeah, I'm positive. I lost an electron. Okay. All right. So here's kind of a summary slide. Okay. Electromagnetic radiation, we generally refer to it a lot of times as light. Visible light is only a small part of that. And again, as I talked about, make sure you know these relationships between frequency. Also know the symbols, frequency, wavelength, and of course energy. And there's our 3 equations I hinted at. 2 of them are written together, where it has E is equal to h nu and E is equal to hc over lambda, but that's really 2 different equations. And there's our relationship between frequency and wavelength. We all like fireworks, right? Who doesn't like fireworks? This is really not necessarily fireworks, although they were around, but what we're going to see on the next slide really kind of started this idea about light and where does light come from when we heat up or what we call excite an atom. And I don't know why this, oh, I see what I did. So let's at least leave with this today, because if you haven't done these in lab yet, you are going to do flame tests in lab. Did you start these? Thursday, okay, so this is coming, so this is good. We're kind of right on track here. So if we take different substances, the one on the left has sodium in it, and so if we just take a sodium chloride solution and we put it in the Bunsen burner in the flame, heat it up, we're putting energy into that, and we see a bright yellow light emitted, okay? If we take something like copper or barium, and I'm not sure which one this is because they both end up emitting in the green region of the spectrum, green-yellow. So say a copper chloride solution, we put that in the flame, we get a different color, okay? So one, it's pretty darn cool. This is actually a really fun experiment because you just do different salt solutions and you get a different color for each one. Watch out for sodium. Sodium just likes to hang out forever, and you got to make sure to get rid of that before you go on to the other flame test. Along the same lines, you might be familiar with what we call neon signs, okay? Well, the original neon signs were filled with neon, and they were these really bright orangish red signs, okay? Well, now a lot of them are filled with different gases. Some of them might have helium in them, or argon, or xenon, so you get all these different colors. So one thing to leave with for today, depending on what the atom is, we get different light emitted. So that tells us that, well, what it's going to tell us is where the electrons are in the atom are going to be different for each element. And that shouldn't surprise you, because each element is different, right? Different number of protons, different number of electrons. We don't expect the electrons to be in the same location for each atom. And that's why we see different colors of light emitted, because of different energies of those electrons. And that's what we're going to get into. We're going to start looking at energies of electrons in an atom. But it's light that lets us figure that out, or lets scientists figure that out. Okay, I'm going to call it quits for today. I think it's time anyway. Thanks for hanging with me. The semester is getting rolling now. I'm sure does anybody have exams this week? Oh, yeah. This is usually like the first week for exams. Finally, the semester is coming. First 3 weeks are usually nice and happy, and then reality sets in, unfortunately. All right, well, have a good day. Attendance sheet,